your attention. Without further delay, let's begin our session. I would like to introduce our speaker, Mr. Ketan Upadhyaya, who will drive all of us with the fundamentals and mechanism of high temperature hydrogen attack. With over 33 years of experience in process industries, including refinery, fertilizer, and petrochemical sectors, Ketan sir has rich expertise in failure investigation, damage assessment, HTHA assessment, and fitness for service. He has developed innovative techniques to extend the plant life of process industries, demonstrating a profound understanding and application of advanced engineering solutions. Over to Ketan sir.
Good morning, everyone. Thank you, Moksha, for a nice introduction. We'll start. Let me share my screen first. For joining with this webinar. This is a complimentary webinar, of course, but you will get certain knowledge about high temperature hydrogen attack. Definitely, it is going to benefit you some way or the other, either by knowledge or by saving certain failures in your plant. Let me start with this failure first, because there were many failures occurred prior to this, HTHA that was found. The first, the latest one that was having a very severe problem was from Tesoro Refinery, and it's the source from Wikipedia. Of course, there were news about it, located in Washington, USA. Some casualties were there, and it ended up with $39 million worth of, compensation with the persons who are there in the public, and it was because of the HTHA, that is high temperature hydrogen attack. Another incident was in India. I won't name the company, but that's a methanator outlet line that was in a fertilizer company, and that also resulted into fire and secondary damages to the equipment. One of the other companies from Kuwait that had a failure of a tube, water wall tube in a power plant. So these are all because of the HTHA. As we understand, HTHA is not limited to certain segment of the companies. It is widespread, like it's like in refinery, fertilizer, chemical, or power plant, or anywhere there is high temperature hydrogen which is being used. Other incidences which are reported as per the API 941 is from Nelson's curve. If you can understand that, there are various curves which are provided for that. And if you look at it carefully, of course, see over here, these are different curves for carbon steel, for 1 chrome steel, for P11 grade, P20 to P12 grade, or P22 grade, and 6 chrome grade. And these are the reported incidences. And we can understand this from this year, this category. We'll discuss this in detail later. But let us understand what is hydrogen. Okay, hydrogen we know as fuel. It's a very important part of human life itself. And we are using this hydrogen on day-to-day activities in our life. Use of hydrocarbons, however, is permitted up to 90 megapascal room temperature, this pressure, as per ASME. Generally, it is used up to 14 megapascal at room temperature in the cylinders. Like 200 bars is the maximum one. And we can see there are CNG cylinders which are carried on the road. And they are also made of steel, as well as they are also made of fibers. But we are talking about the steel cylinders in domestic application for this particular application. Next, we can see this, hydrogen, which is used at ambient temperature for fuel cell. Now, this is not new. We are using hydrogen as battery power. And this is a direct electrical conversion from hydrogen, okay, to form the electrical current, and the appliance is working on that. So storage of hydrogen is essential for that purpose. It may be pressurized. Higher the pressure, higher is the hydrogen storage possible. So that is the principle. You want to increase the size of the battery or the operating period without recharge is very important. Third one, in public service, we can say there are buses, forklifts, bicycles, canal boats, and so many other vehicles which are moving on the road. And in fact, there are ICEs, that like internal combustion engines for hydrogen, which are invented by Toyota, which are having these like cars, hydrogen cars. These are referred to be green hydrogen. So hydrogen is a friendly material to us, right? Why it is creating some problems? That we need to understand. You know, which are the types of hydrogen related damages? Number one is that like weld cracks, and there are blisters, there are hydrogen embrittlements, and hydrogen induced cracking. Now these are all related to somewhere a little bit high temperature, but not exactly at the high temperature. They are room temperature problems. And high temperature hydrogen attack is the one which is at the high temperature. To understand what exactly hydrogen causes within the material, we have to refer to this slide. And coming back to the school, the atomic radius of iron and carbon is important to understand. Here there is a red dot which relate to hydrogen, and a blue cloud which is indicating iron atom. So if we compare this atomic radii, that's for hydrogen it is 25 into 10 raised to minus 12, it's like nanometer, picometer. Then there is iron atom which is 140. You can consider this size difference which is 6 times. So the iron atom is 6 times higher, or hydrogen atom is 1/6 of the iron atomic radius. When there is a little bit of gap between the two iron atoms, the hydrogen is likely to permeate within the material. And the molecular hydrogen, that is H2, is having not the same radii as like hydrogen atom, of course. That is why it cannot permeate into the material. What we need is the H plus, that is nascent hydrogen. Now, how can we generate the nascent hydrogen? There are ways and means to generate, and there are ways and means even if we want to stop, we cannot stop it to generate. So this hydrogen assertion requires its atomic state from molecular stage. H2 is not permeable. We need H plus. And high temperature, high pressure, clean smoothness of the steel surface, angle of the attack, and these are the parameters which are creating higher permeation rate into the material for hydrogen. So hydrogen permeation, as I discussed, increasing temperature will increase the entropy and increase the covalent bond distances. What exactly happens? The temperature, as we mean, the temperature is a filling. By definition, temperature is like kinetic energy of the interatomic distances, or the atoms themselves as kinetic energy. And the distances would vary widely depending on the temperature. Higher the temperature, higher are the distances. When the two atomic uh, elements which are having a wide distances or higher distances, there is a wider gap. When there is a wider gap, there is a vast possibility for something to get entrapped into that between these two. So hydrogen takes chance for that. Yeah, okay. So higher kinetic energy of the atoms results into higher diffusion rate. Then higher pressure, when there is high pressure on the side wherever there is hydrogen, it also leads to higher partial pressure. So higher the partial pressure, it reaches within the material easily, and then finally it starts reacting with the carbon content to form certain hydrogen related issues. Now, just to understand, atomic hydrogen gravitate to the areas of high strain. High strain, that means those areas which are strained or stretched. Favorable internal surfaces features are like inclusions in the steels, grain boundaries, dislocations, and heat affected zones. What happens once the hydrogen reaches inside is that it forms methane gas inside by dissociating the carbon which is bound with Fe, that is forming perlite, the carbide. Okay. So those iron carbides are dissociated from the perlite region to form Fe and carbon. That carbon is now reacted or gets consumed with formation of methane gas when it is associated with hydrogen. And in this process, there is a very high level of volumetric expansion that takes place, as we understand. So this is a cloud of something related to a hydrogen reaction with carbon, and then it increases its size to a tremendous level. It's said to be like more than 800 times volumetric expansion that occurs. And this volumetric expansion pressurizes the internal structure of the lattice, and then it will create certain cracks. Now, let us not jump into that directly. We'll understand this elevated temperature methane formation first. The reaction of the methane formation is thermodynamically favorable at high temperature. That's first. It produces the zones of decarburization. That means the Fe3C, once it is dissociated, then Fe and C forms. When Fe and C forms, the carbon dissociates, and then it becomes decarburized when it combines with the hydrogen, forming methane. So whatever carbon was there within the steel is actually not in the steel in itself. It has formed a gas cloud. It is now pressurized, and now it will start creating certain cracks of the micro movements into the lattice. The decarburization grows inward as a function of the mobility with respect to time and temperature. And carbon concentration gradients at the decarburization zone then will drive the carbon toward the hydrogen rich surfaces. Okay. So ultimately, the decarburization, that is dissociation of Fe and C, carbon moving towards hydrogen, hydrogen binding with the carbon, forming gas cloud, is the decarburization process. We can this understand visually looking through the microstructures like this. In this picture, if we look at it, so this is the area decarburized zone. This is a decarburized zone, and here up to like 4 to 5 grains depth from the surface which is facing the hydrogen, and these are the carbides. Otherwise, we can say they are the perlitic regions which are dissociated from started dissociating from the Fe3C. So how in advanced stage it will affect is that atomic hydrogen accumulates at the grain boundaries and inclusions. So inclusions are those sites which are the attraction point for these gas molecules. Hydrogen then recombines to form the molecular hydrogen. Then hydrogen reacts with the carbon producing methane. Now, this creates insignificant internal pressure, as I explained, within the lattice, and then it will create internal separation within the grain. So what will happen is that some cracking will start. It's termed as fissuring. Now, these fissures are also visible in microstructures. These areas like in this region, we can say over here, sorry, yeah. So this region, these are the cracks, fissures. These are the fissures. We can see these are the fissures. These are the cracks. Now they have become visible in microstructure. So they are still at a micro level. So if we consider this to be something like 100x in magnification, this width is a few micrometer wide. It's not visible by our eye, but it is visible in the microscope. These are the areas which is decarburized zones. And as the decarburized zone increases, okay, the more chances of hydrogen penetrating into this region leading to methane gas formation. And then it continues for formation of internal cracks. So these fissures, internal cracks, fissures, they form. These are the advanced stages of that. This is otherwise normal ferrite pearlite structure. So up to this depth, the material has affected. That's what we can say, looking to this microstructure. And this is the electron microscopy image. And here we can see there are cracks which are running like this. You can see these are the cracks. This is the pearlite region, and this is degraded, and there are cracks which are going through. There are big cracks, there are fine cracks, but there are many cracks. So they are fissures. They are micro cracks, they are fissures. And then these are the results of catastrophic failure. Importantly, this is one of the boiler tubes that we received for the investigation. Importantly, you have to consider there is no thickness loss. Okay, there is no wall loss which is associated with this type of failure. It's like a brittle and sudden failure. It's a very wide opening. And the level of, the extent of the back thrust it will generate, it will create secondary damages to the boiler, even to the other equipment which are there in the plant. So now we have to understand we have understood what is hydrogen damage, HTHA, how it occurs. We really need to understand stage wise what API 941 says about it. How can we do the inspection, or how do we plan the inspection? And is there any way for life assessment or fitness for service? These are the topics to follow. So let me introduce to API 941 that it summarizes the results of the experimental tests and actual data acquired from operating plants. That is API 941. Initially, it used the Nelson's curve for, and Nelson is the person who established various examples or illustrations from the companies or different working plants, and he established one curve for different materials. And those curves are all known as Nelson curve, and they are referred into API 941. So API 941 establishes a practical operating limits for carbon and low alloy steels in hydrogen service at elevated temperatures and the pressures. Okay, but it does not cover for the steels for hydrogen operating below 200 degrees Celsius temperature. Okay, so in 1949, Nelson's diagram was published by American Petroleum Institute. Nelson's diagram is a collection of equipment successes and failures related to HTHA over a wide range of temperature and hydrogen partial pressures over different materials. And then in 1970, first edition of API 941 was released with this curve. This data published in 1970 by APA was revised in 1983 because there was a major problem for material related issues. Those materials which are referred to be carbon half moly, very well known material at that time, like in 1960s and 70s, carbon half moly was a very famous material for combating HTHA. However, this data has been revised, and now carbon half moly is treated as good as it is a normal carbon steel. It's no more HTHA resistant material. So those plants or those facilities which are operating at very old plant setup, and those equipment which are still handling this carbon half moly and at high temperature having hydrogen service require trigger or caution for inspection. That goes without saying. Okay, these are the different curves in provided in the Nelson's curve. This again I am showing is 6 chrome half moly, 2 chrome, 1 chrome, and carbon steels. The curve for carbon half moly was somewhere over here, and that has been removed. Now, from this curve, we have to understand on the y-axis, both sides, left side it is in degree Fahrenheit, right hand side it is in degree centigrade or Celsius. Bottom of the x-axis is in partial pressure in form of PSI, and on the top it is in megapascal. So x-axis represents pressure, partial pressure of the hydrogen. Y-axis represents the temperature. As we understand, lower the temperature, that is on the bottom side of the curve, nowhere HTHA is possible. But as the temperature increases and as the partial pressure somewhere touches around like in all the ranges between 500 psi to maybe very high 13,000 psi everywhere, 500 onwards, it will start creating problem for carbon steels. So when the temperature increases above 210 or 220 degrees Celsius on right hand side, or maybe like 500 Fahrenheit, this problem will trigger into carbon steels. And carbon half moly materials are equivalent to that. So any of the equipment in your facility operating at somewhere around 300 degrees Celsius, 350, 350, 3, 400, 450, they are all vulnerable for HTHA when high pressure as good as like This is 3 megapascal, that is 30 kg, or maybe less than that, 10 kg, 12 kg per cm square pressure. They are vulnerable for this type of damage. Okay. Now, we also need to understand before this hydrogen going inside and creating HTHA problem, it will take certain time. It's referred to be incubation time or incubation in itself. So what is incubation? So hydrogen diffused into the steel react with the carbon when the detectability is microscopic. That is, it cannot be detected by current non-destructive evaluation methodologies and even with the metrographic technique. That is the first stage of that. Then there will be a surface decarburization. Then there are internal decarburization, and then there will be fissuring and cracking. So this is how the hydrogen will create a stage-wise, appearance. But the first incubation period, which is not detectable, whether the equipment is undergoing any damage because of HTHA, within that incubation time, you cannot detect it. So this is again pictorially presented by APA 941. So initially there are decarburized zones, then there are micro cracks and fissures which are forming at the grain boundaries, and then there are macro cracks and material failure that will lead to cracks. And across the thickness of the material, if we refer to that, then this type of fissures or this type of parallel cracks will likely to appear. These cracks generally appear which is perpendicular to the direction of the stress. Normally, hoop stress govern in any of the material, like it's a shell, reactor shell, or piping. So hoop stresses are in the circumferential direction, and they will create a direction which is perpendicular to that, which will be parallel to the thickness. Yeah. Now, to understand what exactly is the incubation period, the incubation period is the hydrogen diffusion within the metal lattice, and it is governed with this equation. Like this is the diffusion rate dt, which is given as do into exponential of the negative energy that is required for breaking of this bond. So that is why it is negative. That's q divided by r into t, where r is the gas constant, universal gas constant, and t is the temperature of exposure. Now, what is do? Do is the pre-exponential term, but it is actually referring the complex things with respect to incubation period is hydrogen partial pressure, the condition of the material, like the state of the material, where are those inclusions, the area of strain, like whether it is HZ or whether it is the other area, whether it is pipe loading conditions, there are equipment which are loaded with the piping loads. So those forces and moments increases the local stress, and those local stress are the areas are generating to local strain within the elastic limit. But that strain is what the parameter reflects as the DO value here, right? And these are the end results. These are the published data which are available from different literatures. These are the graphs that you can determine straightforward for the DT, but this is not the way it should be done, because this is not a straightforward case. In fact, the API 941 has given in next year, too, they have given a perfect graph for those equipment which are operating with carbon half cooling at different partial pressures and different temperatures. And how after how long of this operation, this HTHS was detected into that. So that part is also covered into API 941 as annexures, and we'll later on touch upon to that to find out what is the life of that. Okay, but for now we have to understand what is incubation. Looking to this equation, there are two things which are differing. One is DO and other one is T. The activation energy required Q will also vary depending on the type of material. So if it is like P11, P22, 6 chrome or carbon steel, Q will be different. The temperature will be different. DO is the combination of like partial pressure, the condition of the material, and any imperfections like strain conditions, HZs. Those are representing the DO values. Now, coming to incubation period. These are the microscopic damage which cannot be detected within the incubation period. That is, incubation is you can define as the level where HTHA becomes detectable, but it is still undergoing, but it has not been detected. Once it becomes detectable, that is definition of that, which is given as per AP 941, is 1000x magnification of the microstructure. So damage becomes optically detectable at 1000x and lower magnification, okay, and lower, like it's like 500x, 200x, 100x. Then possible detectable by advanced ND, like PAUT, TOFD, and then otherwise mechanical properties, if you taste it destructively, then are partially affected. What are the mechanical properties? Which are the mechanical properties? Those properties are like tensile strength, but importantly, it is impact or ductility, because it creates problem with related to quick brittle fractures. So that is one. Rapid deterioration of the mechanical properties with fissure growth. So higher the number of fissures or higher the thickness which is being affected within that pipe section or plate section, it will create lower and lower mechanical strength. And then there will be compromised mechanical properties to a level where a macro crack will also result. That you can see without uh, any appliances. So that we can see. And the final stage, of course, it's a failure. And that's the too late part of that. So coming back, we can detect this comfortably, but it is too late. You have no time to use it. If you go at the stage 3, that is rapid deterioration of the mechanical properties with fissure growth, you need to really understand by some various UT techniques that we will discuss as per API 941. But if it is detectable by method 2, if you are at the level 2, at least you will get some, makeshift arrangement period by the time you get another equipment ordered and delivered. So what are the target inspections for HTHA detection? Let us, these are also, I mean, all these things are based on API 941. I'm explaining 941 in detail. Inspection for the HTHA damage is also, it's very important to understand, also what? Also necessary for those equipment which are operating infrequently above the temperature or partial pressure curves mentioned in the Nelson's diagram. That means in the Nelson's diagram, suppose P22 material, it is showing 1000 psi partial pressure and, the temperature level of somewhere around say 350 degrees Celsius is our limit. So below that and lower than this partial pressure, HTHA is unlikely as per Nelson's curve. But this is a curve. These are the theories. But even though some of those times when this condition is breached occasionally, infrequently, then it is the time to inspect. So looking to the DCS records for all those equipment, including those P22 materials or 22 grade, if the temperature either or the pressure or both have breached that condition, that particular curve condition, then it is time to inspect. That is one. That is the inspection target as per APA 941. Next, carbon half moly equipment, even if it is frequently or infrequently, whatever way, they are to be treated same as like carbon steels. So any of those equipment materials having carbon half moly must be treated as carbon steel, and those are to be inspected right now. Right now, if you have not inspected. After prolonged usage, the frequency of the inspection is to be increased. This is what API 941 says. But how much more? That will come into FFS assessment or life assessment. That we will cover in a next slide or couple of slides later. Okay, so these are the operating conditions for carbon half molecules that experience a high temperature hydrogen attack below the below the half mole steel curve. Okay, these are the instances which are Of course, this is from API 941 again. Degree centigrade temperatures, megapascal, which is the hydrogen partial pressure, and then service hours. Okay. So these are the instances where materials failed already, failed or exhibited cracks. If it is not catastrophe, they exhibited cracks and advanced stage of damages, which are below the curve limits. Okay. So this is the another way of the presentation for 1 chrome half moly steel. This is the curve. This was the original 1 chrome half moly, and this is the carbon steel, which is non-welded or welded, but it is having PWAT. PWAT, you will understand why PWAT is important. Post-weld heat treatment is to reduce the strain levels or reduce the internal stresses, residual stresses. When they reduce, obviously, the hydrogen migration level or permeation will be reduced. So inspection targets, the first inspection, it is known fact that material showed HTHA below applicable curve limit. Determination of incubation time is of prime importance to judge the first inspection time. And risk-based assessment study, RBI, helps in identification of the first inspection instance. As I said, if you are having any equipment of carbon half moly, it is the first, right now you have to inspect it if you have not done already. Inspection techniques are some of those which are listed in API and those which are not even listed in API. So early detection possibility is with in situ metrology, and it creates a surface or subsurface impression. The subsurface in metrology, it amounts to very, superficial. It's like 100 to 500 micrometer from the surface and not to a depth which is very high. But any decarburization observed into that, this part, this subsurface part, then it is the time for the incubation time is over now. Okay. Then in advanced NDT methods, which are total focus method for phased array ultrasonic testing. Another is time of flight diffraction method and the high sensitivity WFMK. We'll cover up what are these techniques about. And then at a later stage, the advanced stage, which is detected at by WFMPA or AUBT. Now, this is the metrographic sample in a section view. You can see this is the decarburized zone. This is the edge, left-hand side. This is the edge. This is a decarburized bright white area. This is decarburized, and this is normal ferrite perlite structure. If we see this, but there are no fissure, that means the incubation time is over. If we look at this microstructure from this direction, okay, that is from the surface direction, how it will appear? How will it appear is like this. So this is how it will appear from the surface. So any of these conditions are taking us to conclude that the incubation period is over. Then ultrasonic, this is backscatter technique. If you understand backscatter, these are the backscatter in RF mode that occur because of the presence of the fissures, and higher the frequency, higher will be the peak, and you can detect it easily. But what we need is the sample or like the affected area where you can confirm, because in HTHA, the biggest problem for confirmation by any of those methods like listed as AUBT or PAUT, TFM or TOFD is the availability of the calibration sample. We understand ultrasonic has the principle of setting reference values. What are those reference? Like we are saying 3 mm flat bottom hole or 1 mm side drill hole or 1.5 mm SDH. Those are the reference levels. But those reference levels are not necessarily applicable into HTHA detection because they are different. They are quite different than those which are conventional cracks. No, HTHA cracks are quite different than the conventional cracks. They are micro level and they are quite segregated. They are quite apart from each other. They are not forming a single plane of crack like lack of fusion or like one crack which is growing from somewhere like fatigue crack. So they are quite different. And to detect those type of things, we need calibration block, which is equivalent to that. Or in other words, we can have HTHA affected sample itself as one of those calibration blocks. Now, these are the methodologies for with respect to ultrasound techniques. One is velocity ratio, then attenuation measurements, longitudinal spectral analysis, and this like angle beam spectrum analysis, or conventional single beam, single element A scan backscatter. That's what I explained in this. This is a backscatter one, high frequency probe that you can use for detection of this. But the detectability with these methodologies listed in API 941 is at the advanced stage of HTHA. It is not at the beginning, like when the incubation is over. No, you can't detect with these techniques. So these techniques are listed here. One is time of flight deflection. So this principle wise, if we understand this, one of the transducers is transmitting the pulse, and that pulse of the sound is reaching from one end to other one. In between, if there are cracks, then that crack will be hit by this sound, and it will generate its own bang over there. Like when we are hitting something on a piece of metal, then it bangs ting like that. So that is what frequency response, which is it is generating on its own. So all those cracks will also generate frequency response, and the time difference between the first this pulse that reaches to the other transducer and the subsequent other one. And this is the principle behind using the TOFD, that is time of flight diffraction. Okay, so this is how it goes. So it creates a bang, and then it will be detected. And this is the result. We can see this type of signatures which are representing the HTH. Okay, of course, we can go with the A scan later on, or PAUT to determine, or in situ metrography to confirm that physically. So these are the ways TOFD will generate certain patterns and indicating presence of HTHA. Another method is PAUT, phased array ultrasonic. Now, what ultrasonic by means, we are all understanding since ages old that one crystal is used, which is having certain own natural frequency, resonating frequency, and at that frequency, the sound will will emitted into the material, and then it will reflect back, or either it will be reaching to the other transducer. But in PAOT, we can literally steer the sound. Steering in the sense like we can maneuver this. We can make it left, we can make it right, we can focus it, we can spread it. So these things are possible by the help of multiple crystals which are packed in one particular package. With advanced these electronics, these Olympus make, or even those very well-known companies are there. They are now making this type of steerable ultrasound methodology electronics, which is referred as phased array ultrasonic testing. So we can steer the sound in any directions, and we can have one sweep, like it is moving from 30-degree angle to 60-degree angle 5 times or 8 times in a second, or maybe like 100 times in a second. This will keep on occurring like this. So we can have one single crystal, okay, one single unit rather than crystal, one single unit which will be sweeping all 30 to 60-degree angles and will generate the image. So this is the type of equipment which is like PAUT, total focus method, where in total focus we can focus it like in this direction, or we can steer the sound such that the wavefront is not at certain angle, but it is in 0 degree, having this type of focus. That the total focus is towards the ID surface. That is what it means. Then there is another method which is referred to be high sensitivity wet fluorescent magnetic particle inspection. This HSWFMPI is nothing different than normal WFMPI, except that there are things which require surface preparation prior to inspection. Normally, WFMPI requires buffing and then inspection, but here it requires abrasive blasting and the grinding removal with up to 0.7 to 2 mm of the surface. Okay, that is subsurface, that it will create the subsurface to appear on the surface, and the metal rough polishing to be done up to 100 grit polishing. Then that surface is to be etched with certain acids. Like for carbon steels, it is nitrile, 4%, 8% nitrile can be used. And then we have to do MPI. So that anything which is there will be clearly visible. So it's increasing the sensitivity of the WFMPI. That is why it is high sensitivity WFMPI. So there are limitations for these techniques. First, we'll look at the WFMPI. Useful in HTHA detection after crack formation with high confidence on detect conformation and sizing. Cannot detect HTHA features or voids. In HSWFMPI, useful in HTHA detection with randomly oriented incipient early stage. But still, mind well, these are all advanced stage. Late stage HTHA damage with high confidence and sizing. Sizing is important because sometimes when we say, yeah, okay, HTHA is there. So what is the size and what is the extent is very important to understand about the life limiting factor. What are the limitations are for attenuation, velocity ratio, and AUBT? There are certain limitations which is described as per API 941. I'm not talking about the APAUT, TOFD. These are about the normal ultrasonics. It's useful in detection of the incipient stage of HTHA damage. With a combination of these techniques, a fairly good confidence can be achieved about damage confirmation. Moderate sizing is possible with respect to depth, how much depth that has been affected, but not the crack size. Okay, and then it requires standard samples. So high skill levels and pattern recognition capabilities are necessary for this AUBT technique to be implemented correctly. And further confirmation sometimes also necessary by metrographic techniques. Coming to the limitations for TOFD PAUT and focus, that is TFM. It is useful in detection of early stage of HTHA. It is sometimes referred to be like those cracks which are otherwise detectable with microscopic examination only can also be detected by these methods. So we can understand some good amount of time then is available for acting upon for replacement when these techniques are used. So it requires availability of the standard samples for calibration and high skill levels. And dirty steel, like those which are having high inclusion content, we had one incidence of false HTHA positive. Okay, it was a false HTHA positive confirmation because of the TOFD POT. It was in the hydrogen service, but because of very bad quality of the inclusions, it was detected like HTHA. So those are the limitations for it. They are very sensitive. They are very good, but at the same time, something good is also detecting something which is not being detected or should not be detected, but it will detect, and then we will get confused into these results. Okay, so due to the limitations of individual inspection techniques, it is becoming very necessary to use them in combination, not one. Prior to conducting the inspection, it is essential to identify the locations of importance. The best methodology for which is described in API 581 risk-based analysis based on past operational parameters as well as setting the integrity operating windows based on RBI study. So we have one software made for that, AIOM. We will discuss in a few minutes later. So what are those remedial measures? Let us talk about that quickly. We all know that selecting of a better material and then controlling the process parameters have good heat treatment like PWIT, HSHs are bad for that. And the effect of application of stainless steel cladding on inner surface or the weld overlay are those which are probable workarounds if you have very short period of the service life. So this is the AIM software I was talking about, is the tool for HTHA management, I would say, not for HTHA detection. Detection goes with various methods as we discussed earlier. But once we detected or once we have found what is the probability of the HTHA that to occur, that is incubation period. How to calculate incubation period? So depending on the pressure, temperature, the material selection, we can identify the incubation period. So this diffusivity of the hydrogen at different levels for this curve is for say carbon steels, and then this we can determine from this curve. On y-axis we have time temperature domain for parameter for like it's LMP. It's for creep there is LMP. So for HTHA also we have this LMP. This is our own proprietary screenshot, and this will determine with respect to partial pressure of hydrogen what is the remaining life. So this is very essential, and these are the tools and tackles for dealing with HTHA conditions. And just for having this, insight of AIM, this AIM will give us some very good information about the plant condition. We have a complete PFD or P&ID if you need. That can also be incorporated into that. And wherever we click over there, it will come up with that equipment detail, the drawing, what are the past inspection history, and whether it is likely to be, having incubation period within this today's date or not. If it is, then what is your inspection target? Where you should target the inspection? This equipment is very large, like 10 meters or 50 meters or 30 meters long of pipeline. So where do you target your inspection? It is very crucial. So those things are identified by this AIM software, and these are the outputs available. And once it is done, we have this risk matrix available. Green zone, obviously, we understand is good. The red zone is on a high risk. These are made from RBI. The tools which are I discussed from EIM, and for those materials and the operating conditions. So once we know all these things, that if we are in the like red zone, we have to shift towards the green zone, or we know that if we cannot move towards the green zone, then we need to act upon now what to do next or what is the remaining life. So that can be obtained from this. So I think I have covered so many things in a very short period. Otherwise it requires very deep understanding for STHA. I could have also demonstrated so many things, but you are all welcome at TCR Advance, and we'll be happy to demonstrate so many things which are available, tools, tackles, the microscope, the SCM, the EDS methodology, and all this. So thank you very much, gentlemen, for listening me. If you have any questions, we can interact.